Welcome to another video for IB Environmental Systems and Societies. Today is going to be a short video summarizing the essential ideas for Topic 7, Climate Change and Energy Production. The first significant idea is that there is a very large range of energy sources available to societies around the world, and those sources vary in their sustainability, their cost, how available they are in any particular place, and of course, the way that they interact with global politics. The next big significant idea in ESS Topic 7 is that the choice of energy sources for a society is controversial and very complex. One of the biggest inputs into a society's choice of energy sources is energy security. Can they ensure that they will always have access to a reliable source of energy? The next big significant idea is that climate change has been a normal feature of the Earth's history, but human activity over the last few hundred years has contributed to massive changes that we have not seen in hundreds of thousands of years. The next significant idea for Topic 7 is that there has been significant debate about the causes of climate change. This has been true in the past, but today in 2023, that consensus is almost 100% complete. The next significant idea for IB ESS Topic 7 is that climate change causes very broad, widespread, and significant impacts on a global scale. Those impacts, of course, affect environmental systems, our water and our biological productivity, as well as societies, the people, the cities, the economies. That's why this topic goes so well with your other Group 3 subjects in the IB Diploma program. The next big idea in Topic 7 is the idea of mitigation. Mitigation is how we reduce the causes of climate change. This ties into those 3-tiered pollution management strategies that we first learned about in Topic 1.5. Another big idea in Topic 7 is adaptation. Even if we were to stop producing all carbon emissions today, the time lags of Earth's systems mean that the climate would continue to change for several hundred years. Therefore, it is absolutely imperative that human societies learn to adapt or change in response to a changing climate. That's it for today. Thank you for watching. Welcome back to another video for IB Environmental Systems and Societies. Today's video is the first part about Topic 7.1, Energy Choices and Security. The first big idea is that every energy source available to societies vary in how sustainable they are, how available they are, how much they cost, and then the social, political implications of that society's relationships with other societies on our planet. Most of humanity's energy supply comes from fossil fuels. That's been the case for many years and will continue to be the case in the future. There are several reasons for that. The biggest probably being that all of our existing energy infrastructure is based on fossil fuel extraction and use. However, low carbon energy sources continue to grow and expand. In this graphic that you can see on the screen, it shows that the proportion of coal for electricity generation is expected to fall somewhat, whereas this column here, representing renewables, is expected to grow and grow rapidly in coming years. Again, let's come back to this big idea, right? Energy sources vary in their sustainability. A lot of time when people think of sustainability, they simply think of environmental impact. But remember, this class is environmental systems and societies. So a big part of sustainability usually includes economic and social sustainability in addition to environmental sustainability. So with that 3-factor lens, discuss the sustainability of each of these energy sources: coal, oil, natural gas, nuclear, geothermal, solar, hydropower, wind, biomass. And the sustainability of each of those may be different for each society. And energy sources also vary in their cost. This graph shows the average per megawatt hour cost of electricity produced by a range of different sources for the last 14 years. If you look at this graph, you can do a quick analysis. which source has seen the greatest drop in price. That corresponds with this yellow line right here. Those are your solar panels. The source with the greatest increase in that time is probably this green line right here, which is nuclear. That cost, that changing value, will influence the choice of energy sources by any society. One of the things that you should be able to do, and which you might be tasked to do on an IB ESS exam, is to evaluate the advantages and disadvantages of different energy sources. I recommend that what you do at this point is pause the video, make a copy of this table in your notes, and take some time to research from reliable sources the total global reserves, how much power each of these produces. You might call that energy density. Generally, the carbon emissions, again, on kind of a per unit basis, how transportable each of these are, and then their global distribution. So maybe not how widely they're transported around the world, but where they're actually found or located as a source around the planet. You may also be asked to discuss the factors that affect the choice of energy sources adopted by different societies. Here, I've simply chosen 8 countries, not entirely at random, but these are a good place to begin your discussion. Which energy sources are most available to each of these 8 countries? What's their main energy source that they use? Are those the same or are they different? And then the third part of that discussion is, what are the socio-political influences and implications of their choices? I just found this infographic at Visual Capitalist that evaluates the sustainability of different societies' energy choices, and it's based on equity, sustainability, and security. I suggest you look this up. I'll put a link to it on my website so you can find it later. But I think this graphic would provide a great intro to a debate or discussion about different societies' energy choices. That's it for topic 7.1, energy choices and security. Thanks for watching. Welcome back to another video for IB, environmental systems and societies. Today, we're going to focus on the second part of topic 7.1, energy choices and security, energy security. The big idea here is that energy security is really complex. At times, it's quite controversial, and each country is going to make different decisions based on their own unique circumstances. In my previous video, I presented these 8 countries as mini case studies for you to look at. I suggest that you go through this setup that I showed you previously and suggested that you fill in, and have a look at these 8 countries in particular. Saudi Arabia, as you might guess, one of the world's largest petroleum producers, that availability and depth of involvement is going to affect the choices that Saudi Arabia makes. China, massive coal producer and consumer. Ethiopia and Egypt, both of these countries rely on the Nile River for a lot of different things. Here's where a lot of topics in ESS begin to become intertwined. In topic 4 about access to fresh water, we examined Ethiopia and Egypt as a case study of places where there's potential conflict over access to fresh water. Well, the Nile River is also a major source of electricity for both of these countries, Egypt in particular. Ethiopia has been building a new dam on the Nile, and that has implications not only for the water available for Egypt to produce their own electricity, but also for access to fresh water, as well as terrestrial food production in both countries. So here we have topic 7, topic 4, and topic 5 in the ESS syllabus all intertwined. Iceland is probably the best example of geothermal energy on the planet due to their unique situation on the mid-Atlantic ridge and access to undersea volcanoes. Norway has traditionally been a petroleum powerhouse, but has made a societal decision to try to move away from their petroleum reserves in the North Sea. Costa Rica is developing a reputation as one of the most energy sustainable societies on Earth. There is a case study in a recent ESS exam asking students to evaluate their move towards sustainability. It's not been perfect, but this is a really good case study to dig into more deeply and find out about their energy supplies. I currently live in Cambodia. Cambodia has a lot of potential energy sources, produces a fair amount of hydropower, but also imports a significant amount of electricity from other places. So there are some societal factors that impact Cambodia's energy choices as well. The advantages and disadvantages of different energy sources here on the left play a significant role in a given society's energy security. In particular, the reserves, how transportable those reserves are, and where the energy sources are found. So when you have a look at this matrix that hopefully you set up after the last video, use this to input into your evaluation of a given society's energy security. In my previous video, I shared this infographic showing the equity, sustainability, and security of energy choices for different countries around the world. I suggest that you click on the link, which is available in the comments below, to look at the security information for those 8 countries above. Energy security depends on having enough reliable and affordable energy so that a country can be independent of what happens elsewhere in the world. That's a big part of energy security. Just like food security for a country is that country's ability to grow enough food annually to feed its own population, the same premise applies to security. Is a country or a society able to produce enough electricity to meet the needs of its population without relying on energy brought in from another country or another society? So on this map, the dark red colors are the most energy secure countries on Earth. You've got Australia, New Zealand, the United States, and Canada are the most obvious ones, but you also see plenty of energy independence in Europe, with Norway, Sweden, and France being the darkest red there. The darkest brown are the opposite end of that spectrum. These are the most energy insecure countries on Earth, and you'll notice that those are concentrated primarily in Eastern and Southern Africa. Those have significant geopolitical implications as well, because as these countries wish to move into a more energy secure state, they will seek assistance from places that may have greater energy independence. And those countries can then use that as leverage, political leverage, over these countries. It's basically negotiating from a position of weakness. Energy choices adopted by a society or a country, of course, are influenced by how available they are, how sustainable they are, what type of scientific and technological developments are happening, cultural attitudes, right? And those attitudes change. So do the political and economic factors that feed into these choices. When I was growing up in the 1970s in North America, there was a massive fuel shortage for many years, the oil embargo from OPEC, and that influenced the price of fuel to a way that it actually changed the driving habits and the purchasing habits of many Americans over the types of cars that they drove. It ushered in an era of much smaller and more fuel-efficient vehicles in the United States. That era endured for a while, but has regressed somewhat as the energy embargo recedes further and further into the past. One of the ways that a society can make itself more energy secure is by improving the efficiency of its energy use and consumption. One of the ways that they can do that is by improving their energy efficiency. It means they're still producing the same amount of energy, but they are using it more effectively to achieve the same goals or accomplish the same ends. Another way to achieve greater energy security is to improve conservation. In other words, to use less energy. Frequently, better efficiency contributes to energy conservation. It's also about changing behaviors, such as turning off lights or air conditioners when you're not in a particular room or in a particular home. It's about using less energy to heat a home during winter in cold climates, or keeping your air conditioner set at a higher temperature in warm climates so that there's not as big of a difference between the internal and external temperatures of a structure. As you've seen in the first part of this video, the energy security of a particular society or country is not just a local or national issue. It is a genuinely global consideration with a lot of geopolitical implications and economic connections to other societies. What that means is that all nations must get on board if we are to make any real progress on a rapidly changing climate, because climate is also a global issue. A few years ago, I found this visualization from Antti Lipponen that I think does a really nice job of showing the change in temperature over the last 150 years. So as you can see, the cooler colors in the middle reflect average temperatures in different places around the world. And as we become closer and closer to the current day, those colors become warmer and warmer, representing higher and higher average temperatures until we get into the late 20 teens and we see dark reds, which indicate a much higher deviation from the average or global mean temperatures. Okay, we're back to discussing the factors that affect the choice of energy sources. In the first video, we talked about the advantages and disadvantages of the sources. Really, what you should be doing here for energy security is considering those geopolitical connections and how the energy production and consumption habits within a particular country are connected to things happening in other nations. You want to discuss the pros and cons of different factors that affect a country's energy security. So what you should be doing is pause this video, identify a particular country. I suggest using one of the 8 that I put together at the start of the video, state whether that country's energy security has increased or decreased, and then describe how that factor has affected its energy security. And the factors you should be looking at are the supply and demand of that energy source, the total reserves of those energy sources, geopolitical developments, the overarching theme of climate change. You should also consider natural disasters because those can influence a country's energy choices and energy security, as we saw with the Fukushima nuclear incident resulting from the 2011 tsunami in Japan. Again, come back to these same factors and weigh the pros and cons of each of them for a named country. So choose one country, go through these different factors, list the pros and the cons of each, and for each one of those, identify whether the pros outweigh the cons or vice versa, and then come to an overall conclusion at the end. That's what it means to evaluate the energy strategy of a given society. There's all kinds of international mindedness links to this topic. It's predominantly an international topic, maybe more so than some of the other ones that we've looked at in ESS. That's it for the second video of topic 7.1, energy choices and security. Thanks for watching and happy learning. Welcome to another IB Environmental Systems and Societies video. Today's topic is 7.2, climate change causes and impacts. This topic helps us understand not just how our climate is changing, but why these changes are occurring and what they mean for both the environment and human societies. This image behind me shows a global temperature map with warmer colors indicating higher temperatures. This is a visual representation of the warming patterns that we're going to be discussing in this video. So let's get into it. One of the most important concepts to grasp is that while climate change is nothing new in Earth's history, what we're experiencing today is unprecedented. First, let's examine this graph showing Earth's climate rhythm over 400,000 years. 3 key measurements are tracked here: CO2 levels in blue, temperature in orange, and sea level in green. Throughout this entire period, CO2 levels naturally fluctuated but never exceeded 280 parts per million, or ppm. However, take a look at that dramatic spike at the right edge of the graph. That's where we are today, well over 420 ppm. This extraordinary increase has occurred in just the last 200 years, and that coincides with the Industrial Revolution and the rise of our use of fossil fuels. To understand climate change, we first have to be clear about the difference between climate and weather. The desert seen in this slide helps illustrate this distinction perfectly. Weather is what's happening in the atmosphere at any given moment, like those storm clouds that you see gathering in the image. Climate, on the other hand, describes the long-term patterns of atmospheric behavior in an area. So while this desert might experience occasional rainy weather, its climate is characterized by hot, dry conditions year after year. This remarkable diagram shows us one of Earth's most important climate-regulating mechanisms, the global ocean conveyor belt. This massive system of currents acts like a planetary heating and cooling system. Warm surface currents, shown in red, transport heat from the equator towards the poles. As this water cools, it becomes denser and it sinks, forming deep, cold currents that are shown in blue. This process helps distribute heat around the planet, and it influences climate patterns around the world. When we disrupt these patterns through global warming, we're essentially tampering with Earth's thermostat. The relationship between CO2 and global temperature reveals one of the most compelling pieces of evidence for human-caused climate change. This graph compares CO2 levels and temperature over an 800,000-year period. That's an extraordinary window into Earth's past. The blue line shows CO2 concentrations, while the red line tracks temperature changes. Notice how these lines dance together throughout history, rising and falling in remarkable synchronization. This pattern tells us something crucial. When CO2 levels change, temperature tends to follow. While some might argue that correlation doesn't equal causation, 800,000 years of consistent correlation strongly suggests a causal relationship. One of the most visible impacts of climate change is the intensification of extreme weather events. Let's use Hurricane Katrina, shown in this satellite image, to understand why. Think of the ocean as Earth's biggest solar energy collector. As greenhouse gases trap more heat in our atmosphere, oceans absorb a lot of that extra energy. Hurricanes draw their strength from warm ocean water. It's like fuel for these big storms. So when we warm the oceans, we're essentially providing more fuel for hurricanes. And that, of course, leads to more powerful storms. It's a direct chain reaction. More greenhouse gases leads to warmer oceans, which leads to stronger hurricanes. Looking towards the future, these graphs show different scenarios for greenhouse gas emissions and their potential impacts. The colors represent different policy choices and actions that we might take. The red pathway, RCP 8.5, shows what might happen if we continue business as usual, potentially leading to temperature increases of 3.2 to 5.4 degrees Celsius. The blue pathway, RCP 2.6, represents aggressive action to reduce emissions. This isn't just about numbers on a graph. It's about the kind of future we choose to create. This pie chart breaks down global greenhouse emissions by sector. The energy sector, shown in red, dominates at 73.2% of total emissions. But let's look deeper. This includes not just electricity generation, but also energy use in buildings, in transportation, and in industry. Here we see how global trends manifest at a local level, using Cambodia as an example. The graph shows temperature changes since 1925 with a clear upward trend starting around 1975. This illustrates a really important point. While climate change is a global phenomenon, its impacts are felt locally and they can vary pretty significantly from region to region. This sobering map shows potential sea level rise impacts on North America. The annotations tell us that entire regions, including Florida and much of the Atlantic seaboard, could be submerged. This isn't science fiction. It's a possible future based on our current emissions trajectory. Notice how major coastal cities where millions of people live are particularly vulnerable to the sea level rise. When examining the debate around climate change, it's important to look at what the scientific community actually says. This infographic shows that 97 out of 100 climate experts agree that humans are causing global warming. This isn't just a casual survey. It represents a comprehensive analysis of peer-reviewed scientific literature. The small number of dissenting voices often receives disproportionate media attention, and that can create the illusion of more scientific disagreement than actually exists. This pie chart reveals something fascinating about public attitudes towards climate education. Despite the political controversies surrounding climate change, 77% of Americans, that combines strongly agree and somewhat agree, support teaching children about climate change causes, its consequences, and potential solutions. This suggests a real disconnect between public acceptance of climate science and the sometimes heated political discourse around the topic. This seemingly overwhelming graph actually teaches us something important about climate science. Each colored line represents a different climate model projection, and their variation shows why climate modeling is so complex. But take a look at how they all trend in the same general direction, upwards. This illustrates that while there's uncertainty about precise numbers, there's strong agreement about the overall trend. It's like weather forecasting. We might not know exactly how many inches or centimeters of rain are going to fall next week, but we can be pretty confident about the arrival of a major storm system. The World Bank's Climate Change Knowledge Portal, shown here, represents a crucial tool for understanding climate impacts at local and regional levels. The interface lets you examine both current conditions and future projections for nearly every single country on Earth. Notice how it combines different types of data: temperature, precipitation, and other variables to create a comprehensive picture of climate change impacts. This diagram illustrates how climate change affects multiple systems at the same time. From changing rain patterns to species migration to ocean acidification, each impact connects to and often amplifies others in a type of feedback system. It's particularly important to note how these changes affect both natural systems and human societies. It is an environmental systems and societies class after all. Agriculture to human health to economic systems. Let's examine these maps that show projected changes in forest types across the eastern US. What we're looking at is a dramatic shift in biome distribution between 1960 to 1990 and what's projected for the years 2070 to 2100. Notice how the maple beech birch forests that are shown in red are projected to nearly disappear from the landscape. This isn't just about losing certain tree species. It represents a fundamental reorganization of entire ecosystems. These changes happen because different tree species have specific temperature and precipitation requirements. As climate conditions shift, areas that once provided ideal conditions for certain forest types may not be able to support them anymore. This has cascading effects on everything from wildlife habitat to ecosystem services like water filtration, erosion control, and carbon storage. These four maps tell a story about future water availability. Starting at the top, we see projected precipitation patterns, but that's only part of the story. The second map shows projected evapotranspiration, essentially how much water plants and soils are going to lose to the atmosphere as the temperatures rise. The third map combines both of these factors to show the overall water balance. And then the fourth shows how dramatically these patterns are going to change between 2005 and 2099. What's particularly concerning here is that many agricultural regions are projected to experience really significant water deficits, and that threatens food security and ecosystem stability. Take a look at these forest distribution changes over time. You can see a stark transformation. The map comparison shows how climate change is effectively pushing ecological zones northward. This isn't just about forests moving. It's about entire communities of organisms having to either adapt, relocate, or die. Some species are going to be able to migrate. Others may face local extinction if they can't keep pace with the rate of climate change. This raises important questions about conservation strategies in topic 3. Do we try to preserve ecosystems as they are, or do we help species migrate to new areas that will be more suitable in the future? This WWF diagram beautifully illustrates the complex impacts of even a 1.5 degrees Celsius temperature increase on biodiversity. Notice how different species groups are affected differently. 6% of insects, 4% of vertebrates, and 8% of plants are projected to lose more than half of their climatically determined geographic range. This diagram also shows how Arctic ecosystems are especially vulnerable, with the prospect of ice-free summers becoming more and more frequent. These changes ripple through food webs and ecosystem relationships in ways that we're still trying to understand. This infographic shows the interconnectedness of biodiversity loss and climate change. The arrows between different parts show how one change leads to another in a complex web of cause and effect. That's your feedback mechanisms that we've talked about earlier in the syllabus. Especially noteworthy is how changes in one area, such as reduced primary production, can trigger a lot of downstream effects on ecosystem functions. This shows why protecting biodiversity isn't just about saving individual species. It's about maintaining the stability of entire ecological systems. And that comes back to our conservation strategies that we studied in topic 3. The map we're looking at shows potential coastal flooding impacts, with red dots showing cities of over 10 million people each. This isn't just an environmental issue. It's a massive societal challenge around the world. Consider that these coastal regions aren't just residential areas. They're centers of economic activity, of cultural heritage, and critically important infrastructure. The projected inundation would force unprecedented human migration, and it would require enormous resources for adaptation or relocation. That's a lot of money that most governments don't currently have. This diagram walks us through the process and impacts of ocean acidification, from its drivers all the way through to policy options. As atmospheric CO2 increases, more is absorbed by the oceans, and that leads to increased acidity. This chemical change has profound biological effects, particularly on organisms that build shells or skeletons from calcium carbonate. The flow chart shows how these biological changes cascade through marine ecosystems, ultimately affecting human societies through impacts on fisheries, coastal protection, and food security. When we study climate change feedback mechanisms, we need to understand both positive and negative feedback loops, and equally importantly, their time lags. This picture shows how desertification, biodiversity loss, and climate change are all interconnected. Notice how each process feeds into the others. For example, when climate change increases extreme weather events, this leads to soil erosion, and that reduces carbon storage capacity, which then accelerates climate change further. These cycles can take decades or even centuries to fully manifest, and that makes them especially difficult to address. Let's think about this feedback mechanism diagram as a practical tool. When we examine each arrow and connection, we can identify potential intervention points. For example, the link between the soil erosion and the reduced carbon reserves suggests that soil conservation practices could help mitigate climate change impacts. This systems thinking approach helps us understand not just individual problems, but how they interact and amplify each other over time. This cartoon presents a deceptively simple image of the climate change debate. While it might be tempting to categorize people as either alarmists or deniers, the reality is far more nuanced. The scientific evidence suggests that neither extreme position is helpful. We need balanced, evidence-based approaches that acknowledge both the seriousness of climate change and the complexity of addressing it. This is where our understanding of environmental value systems becomes especially relevant. This slide raises two fundamental questions about climate change for TOK and international mindedness. First, as an international issue, how do we coordinate action across borders when impacts and responsibilities aren't evenly distributed? Second, from a TOK perspective, how reliable are our predictions about future climate impacts when they're based on past data? These questions should challenge you to think not just about the science, but about equity, responsibility, and the nature of knowledge itself. That's it for IB ESS Topic 7.2 Climate Change Causes and Impacts. Until next time, happy learning. Let's get some definitions out of the way first. Mitigation are efforts to reduce the amount of greenhouse gases being emitted into Earth's atmosphere, while adaptation is adapting to the inevitable changes in climate. Let's face it, even if we stopped all carbon emissions today, the lingering effects of the greenhouse gases we've already emitted into the atmosphere would continue to warm Earth's climate for the next 100 to 200 years at least. I really like this image on the screen because it shows a spectrum of actions that people can take to reduce their greenhouse gas emissions. On the left side are the lowest impactful actions we can take, and that includes replacing our incandescent light bulbs with energy efficient LED bulbs. It's easy to do, the bulbs are widely available in stores, and it makes everybody feel good about taking climate action. But the reality is it doesn't actually have much of an impact. The most impactful things we can do are all on the right side of the screen, and that's having fewer children. The reason having fewer children is the number one most impactful action for climate change is that every single person who is born brings their own ecological footprint. They need land and water and air to process waste. They need land to grow food. They need space for infrastructure. They need water for drinking and bathing and food production. Those impacts last many, many years. The next most impactful things we can do is to live a life car-free, to avoid flying all over the place, to purchase our energy sources primarily from green sources such as wind, solar, hydro, and ocean sources. And we can also switch to a plant-based diet where we eat lower on the food chains or at lower trophic levels. Another way to mitigate climate change is to reduce the total amount of energy that we consume. We can do that by using the three-tiered approach to pollution management, since greenhouse gases are in fact a form of pollution. Another tier 2 approach to mitigating climate change is to improve the overall efficiency of the transportation that we use. We're not eliminating the greenhouse gas emissions entirely, we're simply limiting the amount that we release into the atmosphere by improved fuel efficiency. Another approach to mitigating climate change is to reduce the amount of greenhouse gases we emit into the atmosphere. And we can do that by shifting from individual vehicles to mass transit. So even though much of that mass transit may be releasing greenhouse gases, because we are using fewer vehicles, we have more people concentrated on the same vehicle, we are limiting the amount of greenhouse gases being emitted into the atmosphere. Let's not forget agriculture as a major source of greenhouse gas emissions. The cows, pigs, and chickens that people grow in order to eat are all undergoing respiration, and as a result, they release greenhouse gases. They release CO2, they also release methane, which is a powerful greenhouse gas in and of itself. Not only does the livestock that people produce release greenhouse gases, on large industrial farms, the mechanization that we use releases carbon dioxide as well, because most of those mechanized tools, the tractors, the harvesters, the combine machines, those tend to run on fossil fuels. And through internal combustion engines, they release carbon dioxide into the atmosphere as well. A great Tier 1 strategy for reducing our greenhouse gas emissions is to make the switch from fossil fuels to renewable sources of energy. As you can see from the graphic on the screen, about 3/4 of the world's energy sources are currently derived from fossil fuels. However, that slice of the pie dedicated to renewables continues to increase each year as the cost of producing electricity from renewable sources such as solar, wind, geothermal, hydroelectric, and ocean continues to fall, while the extraction cost of fossil fuels continues to increase. Just be careful when you're considering renewables, because not every renewable resource is a zero carbon or low carbon emitter. One of those hidden sources of carbon emissions in hydropower is the use of concrete to construct dams. Concrete is a very CO2 intensive material because of the production of the material and the breaking down of limestone based rocks, where carbon in the form of calcium carbonate has been stored and locked away in a solid form for many millions of years. Geoengineering is another climate change mitigation strategy that people talk about for future generations. It's something that takes a very, very long time and involves the large-scale manipulation or change of global systems. Probably the easiest way to do this is through the process of afforestation, which is the opposite of deforestation. Afforestation means planting forests on a very large scale, because as those trees grow, they remove gaseous carbon from the atmosphere where it contributes to climate change, and they lock it into a solid form as biomass in their trunks, leaves, and roots. Afforestation is a great example of a carbon dioxide removal technique that protects and enhances our carbon sinks in Earth's atmospheric system. That's because forests extract carbon from the atmosphere and lock it away as biomass. If we keep the trees, we keep the carbon out of the atmosphere. Another great way to protect and enhance the carbon sinks on Earth is to focus our efforts at conserving the most biologically productive biomes on the planet. The dark green bands you see here focused around the equator, the Amazon rainforest in South America, the Congo Basin rainforest in Africa, and the tropical rainforest spread across Asia, represent the highest productivity levels on Earth. That means they are most rapidly taking carbon out of the atmosphere and locking it away into biomass, whether it's in the trees or in those nutrient cycles that happen as trees fall and decomposition happens, building up soil matter. One of the climate mitigation strategies that shows up in the syllabus is the idea of using biomass as a fuel source. And the reason that's considered a climate mitigation strategy that reduces greenhouse gas emissions into the atmosphere is because biomass is generally perceived as a renewable resource that can be replenished or replaced relatively quickly. I look at this graphic, and obviously the top parts of the graphic are fossil fuels. They're not biomass. The bottom three are considered biomass, and I'm skeptical of the use of lignite and peat as biomass as a climate mitigation strategy. Peat is undecomposed or partially decomposed biomass that has taken hundreds or sometimes thousands of years to accumulate. So that's carbon that has been slowly building up in a solid form over many, many years. And if we use it as a fuel source, we combust it and we release the carbon that's held in it or locked in it back into a gaseous form. The rate of replacement, the rate of release isn't quite the same as it is with fossil fuels that have been in the ground for 300 million years, but it is a significant difference. So tread carefully when considering peat as an alternative to fossil fuels. Growing crops to be used as a biomass for a fuel source could be considered a tier 2 strategy for climate change mitigation. That's because as plants grow, the process of photosynthesis pulls gaseous carbon out of the atmosphere and locks it into a solid form of biomass where it's no longer trapping heat and contributing to climate change. However, as you see in the cycle here on the screen, the transportation of those crops to a processing facility involve generally the release of additional greenhouse gases through the internal combustion engines of the vehicles. Now, the rate of replenishment of that biomass is quite rapid because crops can be grown annually or sometimes even twice a year. But there's a lot of debate about the net savings from growing crops as biomass for use as a fuel source. So don't consider this to be a guaranteed improvement for reducing greenhouse gases. Earlier we looked at afforestation, the planting and growing of additional trees, forests on a large scale, as a climate change mitigation strategy because as trees grow, they extract carbon from the atmosphere and through the process of photosynthesis convert that gaseous carbon into a solid form as biomass in the plants. That's a geoengineering solution. Carbon capture and storage operates on a similar principle but is generally considered to be an industrial process. So as you see in this image, we have a carbon capture and separation facility, and the idea is that CO2 will be pressurized from a gas form into a liquid form and pumped deep underground. In theory, that sounds great because you're taking gaseous carbon out of the atmosphere and putting it underground in a solid or a liquid form where it cannot trap infrared radiation and serve as a greenhouse gas.